Hello, I'm Itara Kitahara from University of Tsukuba. Today I'm going to talk about dense 3D organ modeling from a laparoscopic video. Laparoscopic surgery is a minimally invasive procedure. Surgical instruments such as the laparoscopic camera is inserted in the abdominal cavity through a small incision. The state of operative area is checked on a display for surgical operations. Due to the advantage for patients, including a small incision range and quick postoperative recovery, it is increasing to use this procedure. On the other hand, surgeons have to imagine the 3D spatial relationships in the abdominal cavity, so it is necessary to consume some time for getting the surgical skills. In order to address this issue, methods are developed to present the 3D information by using AR, MR, VR. Although these techniques require the 3D information of the abdominal cavity, it is still difficult to use CT or MRI during operation. This figure shows a procedure for generating a 3D organ model composed of dense 3D point clouds from monocular laparoscopic images. First of all, the captured laparoscopic video is divided into frames to get multi-view images. Structure from motion (SFM) estimates the sparse 3D point cloud of organ and the pose of the laparoscopic camera. A depth image is generated from the monocular RGB image using deep learning. Finally, a dense 3D model is generated by combining the depth image and 3D point cloud. By applying structure from motion to multi-view images, capturing the organ from various viewpoints, the overall shape of the organ can be reconstructed. On the other hand, because the obtained 3D point cloud corresponded to image feature points, when SFM is applied for laparoscopic images, the 3D point cloud may be sparse due to the textureless appearance of organ. Next step is generating a depth image from a monocular laparoscopic image using deep learning. As training dataset for deep learning to realize a depth image generator, we use pairs of an RGB and a depth image acquired by RGB camera. To adjust the appearance of the laparoscopic image to the dataset, lens distortion is corrected and projective transformation are estimated. This image generation from monocular RGB images is achieved by geometrical transformation and depth generator. To determine the correspondence between laparoscopic and RGB-D images, we capture a calibration board by each camera. In this shooting, the spatial relationship between the calibration board and both cameras must be same. The lens distortion of the captured image is rectified using the board pattern. Then the projective transformation between the two types of images is calculated by referring the detected grid points. Finally, the appearance of the laparoscopic and the RGB image are unified, like this. We use the conditional generative adversarial network CVIM, which was validated for transformations between images in a variety forms. This is a training model for generating a depth image from RGB images. Generator G receives the RGB image and translates it to a depth image. Discriminator D receives the image generated by G or a real depth image and define whether the input depth image is generated or real. G is trained to generate a depth image with which D makes a long discriminate. D is also trained to accurately discriminate generated depth images. After learning G and D with sufficient training data, G can generate a high-quality depth image from an RGB image. So we are going to generate a dense 3D model by combining the depth image and 3D point cloud. This is a process of integrating the 3D information estimated by SFM and the generative depth image. The 3D point cloud is projected onto the depth image. At the same time, the 3D distance between the laparoscopic camera and each 3D point is calculated. By comparing the depth value and the distance of a 3D point, the scale value of the depth image is estimated. By using the scale value, we can generate a dense 3D organ model by back projecting the additional 2D points onto 3D world coordinates. For validating our developed method, we use river phantom with ground-truth data. The clustered model of the river is formed at full scale by a 3D printing of the CT data. We use the laparoscopic camera equipped with a curved tip and an image processor to capture the images at full HD at 60 frames per second. Interior Sense D435 is used for capturing RGB-D images. We constructed a dataset of 288 image pairs. The captured multi-view images are processed using a structure from motion library, ColMap. The reconstructed sparse point clouds are shown as the red dots. Here we use, by applying the proposed method, we generate a dense 3D model as shown in the green dot. In this case, we use pix-to-pix for realizing CGAN. As a comparison target, we densify the point cloud using multi-view stereo, MVS, as shown in the left. We apply the ICP with ground-truth data to the both generated point cloud and evaluate the accuracy by root mean square error, as shown in the left table. In this result, the MVS model is better than the proposed method. However, its densification is not uniform, and holes occur in the model surface, like this. On the other hand, our method achieved uniform densification because the 3D point clouds were generated from a depth image. To evaluate the uniform densification, we divided the 3D model into cubes and counted the points on each one. We also normalized the differences in the number of point clouds among the models. Then the uniformity of the point cloud is calculated as the standard deviation of the number of points. As the right table shows the result, our method has a small value than the MVS model. The shape information which was acquired in uniformity on the surface of the organ is clearly an advantage when considering surgical application. In this presentation, we propose the method for generating a 3D organ model composed of dense point clouds from monocular laparoscopic images. It is not only high accuracy for the entire 3D organ model with uniform density, but also low computational cost. Our method can generate a 3D model in about 7 minutes. MVS requires more than 30 minutes. Thank you very much.